Section 7.6, exponential functions. An exponential function is a function of the form y equals a times bx, where a is not equal to 0 and b is greater than 0, and b does not equal 1, and x is a real number. So here we have examples of exponential graphs. This one represents y equals 2 to the x. Here we have y equals negative 2 to the x. They're flips of one another. Here we have y equals 1/2 x and y equals negative 1/2 x. Remember from previous chapters that linear functions are when we have items for our y values appear to have a pattern of something being added to it by a constant amount. Exponential functions, on the other hand, are when we have a constant amount being multiplied into our y values. As the x values increase by a constant amount, the y values are multiplied by a constant amount. This amount is the constant ratio and is the value of b in your y equals ax or a times b to the x power. So for this example here, notice that our x values are going up by 1, but our y values or our outputs are being multiplied by 3 each time. It's the idea that you're multiplying by 3 each time that tells us that this is an exponential function. So in our first example, we want to tell whether the set of ordered pairs satisfies an exponential function and then explain our answer. So as we look at our x values, we're increasing by 1. But then for the y values, we go from 4 to 12, which could be adding 8. But then from 12 to 36, well, that's not adding 8, so that doesn't work. Or we could be multiplying by 3. So 4 to 12 times 3, 4 times 3 is 12. 12 times 3 is 36, so that works. And 36 times 3 is 108. So our pattern here is that we're multiplying by 3. So that means that this is definitely an exponential function. In the next example, we look at the pattern again. So we've got from negative 1 to 0, that's adding 1. From 0 to 1, that's adding 1. And from 1 to 2, they're adding 1. But at our y values, we're looking, well, from negative 64 to 0, they're adding 64. 0 to 64, we're adding 64 again. And 64 to 128, you're adding 64 again. Since we're adding by a constant, or in this case, adding 64 each time, this is not exponential, it's linear. In the next example, we continue the same thing. We're observing the pattern. So from negative 1 to 0 is plus 1, 0 to 1 is plus 1, and 1 to 2 is plus 1. The y values are going from 1 to 0, which could be, in this case, let's say subtracting 1. From 0 to 1, that'd be adding 1. And from 1 to 4, that'd be adding 3. Well, in this case, the pattern, there is no real pattern. It's random. Since it's random, it's definitely not exponential. And it's also not linear. In the next example, we're checking out the pattern again. So in your x values, we've got plus 1, and plus 1. But then as we look at the y's, we're going from 4 to 2. So we could be subtracting 2. Well, 2 to 1, the subtracting 2 doesn't work anymore, so we'll go back to the top. From 4 to 2, we could also be multiplying by 1/2. and then half of 2 would be 1, and then half of 1 would be 1/2. So in this case, we are multiplying again, but this time we're multiplying by 1/2. And since we're multiplying by the same number each time, this is an exponential function. So in the next example, we're given the function f of x equals 500 times 1.035 to the x power. And this function models the amount of money in a certificate of deposit after x years. They want to know how much money will there be in the account after 6 years. So that means our x value in this case is going to be 6. So we're going to plug in 6 for x into that equation. So we're going to take f of 6 equals 500 times 1.035 to the 6th power. And it's this portion of the equation that we want to plug into our calculators. And we're going to find out that after 6 years, we should have $614.63 in our account. We're going to look at the same thing here. We've got f of x equals 200,000 times 0.9 to the x power, where x is the time in years, and it models the population of a city. What is the population after 7 years? So that means we're going to take f of x, and we know that x should be 7 in this case. So we're going to plug in 7 for x. So f of 7 equals 200,000 times 0.98 to the 7th power. So once again, this is what we want to put in our calculator to figure out what the population will be after 7 years. So after 7 years, the population is going to be right around 173,625 people. In the next example, there are 30 beetles and their population doubles each week. The function f of x equals 30 times 2 to the x power gives the population after x weeks. They want to know the population after 56 days. Well, before we start this, we need to figure out how many weeks 56 days is. So we're going to take 56 divided by 7, and we get this is 8 weeks. So that's what we're going to plug in for x. So we're going to take f of 8 equals 30 times 2 to the 8th power. So once again, we want to plug this into our calculator, and we should figure out that after 8 weeks, the population of beetles is right around 7,680 beetles. In the next problem, it says the initial population of rabbits is 20. It triples every half year. The function f of x equals 20 times 3 to the x power gives the population after x half-year periods. How many rabbits will there be after 3 years? Well, they're talking about half-year periods, and if they're talking about 3 years, that should be 6 half-year periods. So that means x is going to equal 6 in this case. So we're going to take f of 6 equals 20 times 3 to the 6th power. And so this is what we want to put in our calculator. And we're going to get that f of 6 equals, or after 6 years, the population of rabbits is 14,580 rabbits. To graph an exponential function, choose several values of x, positive, negative, and 0, and generate ordered pairs. Plot the points and connect them with a smooth curve. We're going to use the graphing calculator to find a lot of our points using the table feature. So if you don't remember how to do that, make sure you ask for a refresher or you look up the previous videos where we used it. So here we want to graph y equals y equals 0.5 times 2 to the x power. Right? So we have y equals 0.5 times 2 to the x power. And so we want to put this in our graphing calculator under the y equals screen, and then we'll look at the table of values. And so for me, my table of values is going to read out the following information. Well, I'm just going to choose some points. So from, let's say, -2 to 3. And so at -2, my y value is 0.125. And at -1, it's 0.25. At 0, it's 0.5. At 1, it's 1. At 2, it's 2. And at 3, it's 4. And so what I want to do now is plot these points. So at -2, let's just get as close as we can. And then -1. At 0, we're at 0.5. At 1, we're at 1. 2, we're at 2. And 3, we're at 4. And so remember from the previous examples of exponential functions that we saw at the beginning of the notes, they have a nice smooth curve. And in reality, what happens is your graph's going to start to, in this case, is going to grow really fast after a certain point. But the back half, or the left half, is going to get infinitely close to 0, but never cross the x-axis, and then it's going to grow smoothly up and to the right. So it looks something like that. So this is the graph of our exponential function. All right, then let's look at the next one. We're going to use the calculator again to find our points, and then graph them as needed. So we want to graph y equals 3 times 2 to the x power. So we're going to list our points in an xy table. And so when we put this in our calculator and we go to the table feature, let's say I take points from -2, -1, 0, 1, and 2 this time. So at -2, I get 0.75. At -1, I get 1.5. At 0, I get 3. At 1, I get 6. And at 2, I get 12. And so now I'm just going to plot these ordered pairs. So -2 is 0.75, -1 is 1.5, 0, 3, 1, 6, and 2, 12. So that's kind of off the graph. And so now I'm going to connect my points. So as it goes to the right, it's increasing, but as it comes back towards the left, it's getting infinitely close to the x-axis, but never crossing it. And so this is what our graph looks like. Try to make it as smooth of a curve as you can. And so this is our exponential function. The next one, we've got y equals -0.5 times 3 to the x power. So we're going to create our xy table. And so once again, using the calculator, I'm going to grab points from -2 to 2. So -2, -1, 0, 1, and 2. At -2, I get -0.056. It'll be kind of difficult to graph, but we'll try. And then at -1, I get -0.167. At 0, I get -0.5. At 1, I get -1.5. And at 2, I get -4.5. And so I want to plot these points. So at -2, I am really close to the x-axis in this case. At -1, I'm still really close to the x-axis. At 0, I'm at 0.5, so I'm about halfway, which isn't bad. And then at 1, I'm at -1.5. And then at 2, I'm at -4.5. And so in this case, I'm still going to get infinitely close to the x-axis, moving to the left, but now my graph is growing slowly towards the negative end of my graph as it moves to the right. So it's going towards the negative, or it's growing, I guess it's not growing, it's decreasing smoothly but more rapidly as it goes towards the negative y values as it moves into the positive x values. So it looks something like this. And then our last problem, we've got y equals 4 times 0.6 to the x power. So once again, we'll create an xy table. So x, let's say we take from -2, -1, 0, 1, 2. And because I have the calculator, I'm going to grab some extra values, so I'll say 4 as well. So at -2, I have a y value at 11.1. -1 is 6.7. 0 is 4. 1 is 2.4. 2 is 1.44. And 4 is 0.52. And so we want to get as close as we can when we graph these. Decimals are hard to graph, but we'll try our best. So at -2, it's 11.1. At -1, it's 6.7, so right around almost 7, but not quite there. At 0, it's 4. At 1, it's 2.4. At 2, it's 1.44. And at 4, it's 0.5. So this time, our graph is actually decreasing from left to right, and it's getting infinitely close to the x-axis, but this time on the other end of the graph than the last few examples we've seen. So it gets infinitely close to the x-axis, but never crosses it. And so this time, our curve looks something like this. If you ever need to check to make sure your graph looks right, you can always go back to the graphing calculator and look at the actual graph as opposed to just the table feature. And then you'll know whether or not you've graphed it correctly on your paper.